Section 3.1, Part 1, Exponential Functions and their Graphs. In this section, we're going to begin looking at exponential functions. Now, an exponential function is a function where the base is a constant value and the variable is in the exponent. That's what makes it different. So it's not about having an exponent, it's about having a variable exponent. Now, it's important to understand, however, that the base value cannot be negative, so it needs to be positive, and moreover, it also cannot be 1. If it was 1, you really wouldn't have the curve that exponential functions have, since 1 raised to any power would simply be a horizontal line. It would always be 1. So as long as it's not 1, and as long as it's positive, that creates the shape we're talking about. Now, in our first part here, we're simply going to talk about what they look like and kind of sketching them and coming up with some of their properties. So first off, the basic shape looks like this. Obviously, as x increases, so does the power, and as you can see, it just makes things grow faster and faster and faster. Exponential functions really model the idea that the slopes become steeper the higher the exponent goes. Okay, so instead of having one constant slope like a line, we have a slope that's ever increasing. So first off, looking at the graph, the domain will be all real numbers, okay? Even though it kind of starts to look like it goes a little vertical, technically it is expanding out over all x's. Now the range will be above the x-axis. So the y values you get are only positive. And that makes sense because by definition, the base here cannot be a negative number. It also can't be 0. And when you raise any positive value to any exponent, your answer is always a positive number. So the range is going to be basically above. So that creates, as you can see, a horizontal asymptote as you get closer and closer. As x's get smaller and smaller, you get closer and closer to the x-axis. So the x-axis itself is a horizontal asymptote. So a couple important points you want to notice is that when you plug in 0, you're going to get the the y-intercept. And because anything raised to the 0 power is equal to 1, that means that a really common point with many parent graphs is going to be at 0, 1. Because when we talk about just a basic graph of a number raised to a power, that's always going to be a common point they go through. Now, clearly with different bases, you might get a little bit different curvature as far as being steeper or maybe less steep, but going through 0, 1 is very common. Now, obviously, many of the graphs we're going to do will have transformations in them, with this shape being moved left or right, possibly flipped upside down and things like that, or reflected. But a very common point in parent graphs with no transformations going on is 0, 1. So just something to think about. And like I said, aside from that, knowing what the asymptote is going to be very helpful as we make our sketches. So let's start with a really basic example. Let's just graph, f of x equals 2 raised to the x power. So in this case, we don't have any transformations going on. So what we're going to do is simply plug in some easy numbers and make the graph happen. So the first thing we have to realize is it growth or decay? Well, to understand whether it's growth or decay, you want to know what the shape is. So the thing is, in some graphs, like we talked about, they go up like this, okay? And clearly, because we're getting bigger as we increase our x, that's growth. However, there are some exponential graphs that look like this. And those are just reflected in the y-axis. So they have the exact same shape. They are heading toward the x-axis. They're still as a horizontal asymptote. They still can pass through this point, but they're moving down this way. And so as x gets bigger and this is approaching the horizontal asymptote, because it gets smaller and smaller and smaller, we refer to that as decay. So the way you can tell the difference is, well, when you just have your regular exponent with the x or whatever, that's going to look like this. So to reflect it in the y-axis, we need to put a negative with the exponent. So what you're going to know is that when you have a number raised to this right here, just a regular positive exponent, that's going to be growth. If you have a value raised to the negative exponent, that's going to be decay. So you can tell right away about the input which way it's going to be. So obviously here, with a positive exponent, growth, reflecting over the y-axis, makes it decay. So in our question here, 2 raised to the x, because the exponent's positive, that means that this is going to be an example of growth. Now, because they all generally have the same shape, when we talk about the domain for all exponential graphs will always be all real numbers. And of course, in interval notation, that just means we're going from negative infinity to infinity. Now again, this graph right here doesn't have any graph transformations, so we know it's not moved up, down, left, or right, or anything. And so because it's basically a parent graph, and this is kind of what we refer to as just a number raised to x as being a parent graph, the range is going to, again, just be the positive y's, okay? And we know that because the asymptote is going to be the x-axis. So y equals 0 is my asymptote, so the range is going to be all values greater than that. So again, in interval notation, from 0 to positive infinity. Now, we know the shape, and obviously we know kind of where the asymptote and stuff is, so we can mark that in. But to help us make sure we get the right curvature, because different bases obviously are a little steeper than others, we want to come up with some ordered pairs to make that happen. So an easy way to do that is to literally just choose the numbers -1, 0, and 1. Now, these are smart numbers because they're right around the y-axis, and they're not super far either way. Because clearly, if we move too far left, the numbers become super, super small. And likewise, if we move too far to the right, the numbers become really big, really fast. So choosing -1, 0, and 1 are numbers that usually are something we can easily sketch. And not only that, they're also really easy numbers to evaluate in here, especially if you don't get a calculator. So let's go ahead and plug -1 in, 0 in, and 1 into our exponent. So if we plug in -1 in, 2 raised to the negative first is just going to be 1/2, because raising something to the negative first power is the reciprocal. So it takes 2 and flips it over. Anything raised to the 0 power is equal to 1, which we talked about. And of course, 2 raised to the first power is 2. So we'll make the sketch. The first thing, of course, is don't forget to put in your horizontal asymptote. We like to have that visualized. And because, again, this is basically a parent graph, there's no transformations, it's going to be the x-axis. So let's plot our points. Okay, so in this case, we have the ordered pair -1/2. So we'll make a dot right here, 0, 1, and then 1, 2. And again, you can clearly see that this is going to be increasing left to right, which makes sense because it's growth. And again, when you sketch it, make sure you come just off of the horizontal asymptote through these points and make sure you continue to get steeper. So the sketch is going to look something like this. Now let's try an example where we have some actual graph transformations. So when we do this, the goal obviously on this one is to say, all right, well, let's think about what the parent graph looks like, and then we can simply apply our transformations. So when I come up with my ordered pairs here, I'm going to be viewing this as how did we literally move the parent graph to look like this? Okay, so let's start with our basics. The exponent is positive, so in this case, it is going to be growth. So we'll go ahead and identify as being growth, so we know the shape is going to be, increasing left to right. The domain, of course, is all real numbers. That does not change. Now, the range is going to be a little different. So what we're going to do with range and asymptote is we're going to go ahead and figure out where the ordered pairs are first and think about what the transformations. So these are things that are pretty easy to see right away, but we want to think about what this looks like. Okay, so here are the two things we want to do to help us really quick and easy figure out what's going on. First off, let's consider what the parent graph looks like. Now, in this case, the parent graph is essentially this graph with a base, but no other transformation. So the +3 in the exponent and the -2 on the outside, let's just get rid of those. So in this case, our parent graph is y equals 4 raised to the x. And again, you can see all I did was clear out the transformations. So what we're going to do is we're going to figure out some quick, easy ordered pairs for the parent graph here. And then, considering what the transformations are, we can adjust those ordered pairs to give us ones for this specific graph. Further, we can also figure out where our range or asymptote is. Okay, so thinking back to our last example where we just had this basic idea, again, really easy numbers for our exponent is -1, 0, and 1. So plugging -1 in flips it over, so 1/4 would be the same thing as 0.25. 4 raised to the 0 is 1, and 4 raised to the first is 4. Okay, those are very easy numbers. Now, clearly these aren't the ordered pairs for this graph, but because we already punched these up, it's very easy for us to adjust these to make it happen here. So the question is, what are my transformations? Okay, so what we're going to do is we're going to go back to our knowledge of graph transformations and knowing inside and outside as far as horizontal and vertical changes. So in an exponential graph, the x is up in the exponent. So this is kind of the inside part. That's where the horizontal changes are going to be. Clearly on the outside here, -2, that's going to be a vertical change. So because I'm adding 3 on the inside, that means that that's going to give me a left 3 as far as my x's, right, my horizontal part. And because I'm subtracting 2 on the outside, that means I'm going down 2, okay? So we're going left 3, down 2. Now this helps us because we think about what the original parent graph looks like. And again, that just means that the x-axis was our asymptote. It goes through 0, 1. It's got this shape, right? So we're just going to take this picture and these ordered pairs and go left 3, down 2. So that means to get our ordered pairs, since left 3 is the horizontal, we're going to take all of these numbers and move them left 3. So to go left 3, that just means we subtract 3 from them. So if I take -1, 0, and 1 for the x's, and I take each one of those and subtract 3, right, to every single one, that's going to give me the ordered pairs. -1 minus 3 is -4. 0 minus 3, of course, is -3. And 1 minus 3 is -2. So then we need to look at, well, how do the y values change? Well, vertically, we're going down 2. So that means with every single number with my y's, I'm going to subtract 2. So that means my 0.25, 1, and 4, we're just going to take away 2. So if you take 0.25 minus 2, that's negative 1.75. Okay, 1 minus 2, of course, is negative 1, and 4 minus 2 is 2. Okay, so we're always going to lean on the really quick, easy way of generating the parent graph ordered pairs, and then with using our knowledge of graph transformations and how the horizontal and verticals change, we can adjust our x's or y's. Now, remember, the horizontal asymptote on a parent graph is the x-axis. So any vertical change will affect where that is because that's a horizontal line. Because this graph is moved down to, that means that our horizontal asymptote, instead of being on the x-axis, it's going to move down here. So when we talk about what the asymptote is, instead of being y equals 0, again, vertically we take away 2. So this is going to be y equals negative 2. Now, because we know what the asymptote is, this graph, of course, exists everywhere above it. So instead of our previous example where we were basically everywhere above 0, because the graph got shifted down, now this graph exists everywhere above negative 2. So the range in interval notation will go from negative 2 up to positive infinity. Okay, so we considered the parent graph, looked at the transformations, and we filled out our information. So just like before, we want to graph our asymptote, graph some ordered pairs, and make the shape. We do know it's growth, so obviously it's going to be that increasing left to right. So in this graph, we're going to go on to negative 2 and make our horizontal asymptote. So let's sketch that in there with a dotted line. And then, of course, we'll plot up our points. Okay, so in this case, we're going to go negative 4, and then down 1.75, negative 3, negative 1, and then negative 2, positive 2. Now, one thing you should notice about this graph is that's a little bit steeper, which makes sense because the base is 4. In our previous example, it was a 2. So when you compare the shape here to our previous graph, this one's going to be steeper. So if this felt as you would plot these ordered pairs like it was a little steeper, that's definitely the case because having a bigger base here makes it grow larger faster. So if we go ahead and sketch the graph, again, coming off the asymptote up here, we'll just continue up just like that. Let's try one more example, but this time looking at an example with a negative exponent. Now, the thing, of course, about a negative exponent that you should recognize right away is this is going to be decay. So that means when we look at this graph, the general shape I'm thinking about now looks like this, okay? Now, we're still going to view the parent graph because obviously we're going to use our graph transformation to figure that out. But and our parent graph is still going to be thinking just a positive exponent. But again, we can go ahead and move those things around as needed. So let's again figure out what we're going to be doing with our pieces. So in the parent graph, I would, of course, for my exponent, choose negative 1, 0, and 1. Plugging those in, of course, 2 to the negative first power flips it over, so you get 0.5. 2 to the 0, of course, is 1, and 2 to the first is 2. So as always, those are the parent graph, but we need to reflect it. Okay, that's what makes it decay. So that's the negative part, and we need to move it up 3. So that means we're going to basically put a negative for the x's, so that's the reflection, and then we're going to go up 3 for the y's, okay? So that means over here in our x's, make them the opposite sign, and over here, we're going to add 3. So those are the adjustments we can make to these ordered pairs to make this graph happen. And clearly, when you make the x's negative, it's going to make that reflection happen. So while our parent graph clearly looks like growth, it will flip the other way and become decay. Okay, so as we make this happen, we want to plug the right numbers in. So obviously plugging in negative 1, we're going to flip it around, and that's going to become positive 1, because again, we're going to make these all the opposite sign. So that means this will be a positive 1. The opposite of 0 is still going to be 0, and then the opposite of this will be a negative 1. Now the next thing, of course, is for the y values, because this graph has a plus 3 on the outside, we're going to add 3, move them all up. So that means for 0.5, we're going to add 3 to that, and that's going to become 3.5. Okay, adding 3 to 1 is going to give us a 4, and then adding 3 to 2, of course, gives us 5. So again, looking at how we adjust the domain range and asymptote, the asymptote, again, by the parent graph, of course, is the x-axis. Vertically, we're moving up 3. Okay, so that means instead of being y equals 0, adding 3 tells us this is going to be at y equals 3. We're going to move that up. So that means the range is everything above that. So then that was going to be from 3 to positive infinity. And I will point out, of course, the domain is still and always all real numbers. So now that we have our updated ordered pairs by reflecting our x's, making them negative, and moving up our y's by adding 3, we'll go ahead and place all these in here. So the asymptote, again, is at y equals 3 this time. So we've moved it up. So we'll put that horizontal asymptote there. And then looking at our ordered pairs, at positive 1, we're up at 3.5. At 0, we're up at 4, and at negative 1, we're up at 5. Now, clearly, as you can see, looking from left to right, this time the dots are getting smaller, which again makes sense. It should be decay because we have that negative exponent. So when I sketch my graph, it's going to look just like this. And again, make sure you just slowly approach the horizontal asymptote. Now, because we're talking about exponential functions, there is a very important number that's not a nice integer or anything, that is a base we need to discuss, and that's the natural base e. Now, e is, like pi, a special irrational number in mathematics. It's approximately 2.7182818, so on. And it's named lowercase e because it's named after the mathematician Euler, okay? And since Euler starts with e, that's kind of how they named it. Now, we're going to get more into what e really is in the future, but for right now, I want you just to understand it's a special number in math like pi, okay? Pi, there's a special relationship geometrically that creates that. The same is true with e, and we're going to get into more what that is later. But for right now, we just want to understand it's a special number that does come up often with exponentials, and as you'll see tomorrow, logarithms. So we want to start being able to work with this. Now, obviously, when you work with e and being an irrational number, this is one where we would let you use a calculator, okay? Because obviously, we don't expect you to memorize this or do any complicated math with it. So you'll get to use a calculator if you're graphing anything with a natural base. Now, the other thing I'm going to say is, as we do this, obviously, you're not going to be really super accurate with a pencil on paper, so you don't need to round more than one place, okay? So when you see me do my work today, I'm literally just going to round to about the 10th place. And when I sketch it, just do the best I can to be in the right place. So let's look at the example of literally just graphing e to the x. Okay, so basically it's a parent graph, but this base now is the number about 2.718, so on. That's the only difference. Now again, the exponent is positive, so clearly this is growth. The domain remains, of course, all real numbers. Now, there is no transformations. This is not moved up, down, left, or right, or anything. So the asymptote is still going to be the x-axis, y equals 0, which means, of course, the range goes from 0 to positive infinity. Now, here's where your calculator comes into play. I still want to plug in -1, 0, and 1 into my exponent, but clearly that would be a very difficult calculation with an irrational number like this. So we're just going to say, plug in your calculator and round maybe to one place. So plugging -1 in, e raised to the -1st is approximately 0.4. Because again, I can't be that much more accurate with my pen or pencil. Clearly though, 0 will give you 1. Anything raised to the 0 power will be 1. So we do have that one for sure. And e raised to the 1st, again, is e, so we'll just round that to 2.7, because obviously that's as accurate as we can be. So to sketch it, it's honestly going to look like any other exponential. We still have our horizontal asymptote here on the x-axis. Our order pairs are a -1, about 0.4, which is almost a halfway, so that's good enough. 0, 1 for sure, and then 1, 2.7, so about right here. And I'm not going to measure for perfection, so obviously as long as your numbers make sense, that's good. Okay, so again, make sure, because this is growth, left to right we increase, and there we go. Let's try one last graphing example with our natural logarithm, but we'll put some graph transformations in here just to make sure we can see exactly what's going on. Now again, the nice thing about this particular example is because we're using a calculator, we don't need to worry about the parent function and transformations, because if you have a calculator, you can just plug numbers in to the whole expression. So the nice thing about this particular example will be that you can just come up with the decimals and make the sketch. Now again, looking at our exponent, it's positive, so clearly in this it'll again be growth. The domain will be all real numbers. And since we're going to use our calculator to come up with some numbers, let's go ahead and plot some order pairs, make the sketch, and then when we're done, we'll go ahead and look at what that domain and range are. Okay. Now, one thing I will point out, of course, though, is you can clearly see the graph is going to be moved down 3. So one thing I guess you could say right away is we know the asymptote will be at y equals -3. So that's one thing you can put in there. And clearly the range will look like this. So I guess I suppose if you can see just that part of it, that's pretty much a good enough for, range and asymptote since we know which way it goes. Now, again, I'm going to use my calculator. So I'm going to pick some numbers to plug in here. Now, again, normally, I will say in the parent graph, we would choose -1, 0, and 1, and you can try those. But because we're moved over a little bit here, I'm going to choose the numbers -3, -2, and -1. Now, you can just use a little trial and error to get those, but I just looked at it like, well, if we're going to add 2 to every single x, that's, like moving to the left 2, if you will. So that means I'm just going to subtract those numbers to make it happen. So instead of using the -1, 0, and 1, I just went ahead and subtracted 2 from every single one of those. It just makes it go a lot more easily. So using my calculator, if I go ahead and plug those in, plugging in -3 gives me about -2.3. Plugging in -2 is -1. And then if I plug -1 into the expression, you get 2.4. Now, keep in mind, be very careful when plugging this into your calculator. You want to make sure as you do this that the order of operations is preserved. So make sure you're typing 2 times and then hit that e to a power. It's right on the left side of the calculator. You have to hit second natural log button. And then make sure that after you type in the x plus 2 in the exponent, or I should say the number plus 2 in the exponent, that you arrow out of the exponent to type your minus 3, okay, just to make sure it looks exactly like this. Your cursor will be in the exponent when you're there, so if you forget to take it out, you won't get the correct minus 3. So now that I have all this information, we go ahead and plot our points. So I'll go to -3 here and put my horizontal asymptote in. Okay, so then at -3, if we go down about 2.3, we're going to be about right here. Okay, -2 takes us to -1, and then -1, we're up here at 2.4. Now, if this looks a lot steeper, that should clearly make sense, because even though we have the same base e, we're doubling it, right? This is a vertical stretch. So even though we've maintained the same base, this should look a lot steeper than our last graph, because obviously we're stretching it vertically by 2. So if we go ahead and sketch it in here, it's a much steeper graph. So it's going to look something like this. And one thing I will notice is it does become or feel very vertical, okay? It gets, I should say as you sketch it, very large, very fast. So don't feel wrong if you almost feel like you're going almost vertical. They do get pretty steep. Now, one last thing we want to talk about, since we're just introducing and doing the basics of exponentials, is the most basic way of solving. Now, later on, we're going to solve these, some more complicated exponential ones with a more general purpose. But right now in part 1, we're just looking at the basic graphs and their shapes, and also the very basic way of solving. So what we're going to look at is what's called the one-to-one property. This basically is the idea that if you have the same base, right, so some number, and you have it raised to some exponent, and again, the same number raised to a different exponent, if we know they're equal, the conclusion must be those exponents must also be equal. So what we can use as far as a solving technique is we can rewrite an equation to have the same bases, and once that's complete, we can set their exponents equal to each other. So the goal is to look at what you're given and try to make it so you have the exact same number raised to a power on both sides. And then, of course, once that's done, set those equal. So in our first example, we have 9 equals 3 raised to the x plus 1. So what you want to do is look at 9 and look at 3 and figure out, is there a common base that you can write it as? Well, when I look at 9 and 3, I know that both of those numbers are powers of 3. 9 is 3 squared, and clearly 3 is, 3 to the first power. So what I can do is I can rewrite 9 as 3 squared. I can leave the other side, since the base is already written as 3, and make it look like this. So because I have an equation now where the bases are the same, and I know they're equal, that means that this exponent must equal this one. So to solve for x, I can just set 2 equal to x plus 1. So this exponent must equal this one. And in doing so, it tells me that x must be 1. Now, that's very straightforward because I think it's pretty obvious with 9 and 3. However, there are other situations like our second example with numbers like 1/2 and 8. Now, clearly they don't look the same, but in your mind, you want to ask yourself, are there powers of one number that can create both 1/2 and 8? Now, one hint I want to say is don't forget that exponents can be negative and do reciprocals. So when you look at 1/2, you could view 1/2 as being 2 to the negative first power. So when I rewrite the 1/2 as like that, I can make it look like this. Now, when you look at 8, well, my clue is I've already written the left side as a base of 2, and you should know 2 cubed is 8. So instead of writing 8, we can write this as 2 to the third. Now, before we set them equal, we want to make it one single exponent. So as a reminder, when you raise a power to a power, you multiply those things together. So on the left side, this is really 2 raised to the -1 times x. And on the right side, we have 2 raised to the third. So we have common bases. Their exponents must be equal. So that means -x must equal 3. When you divide by -1, we come up with x equals -3. Now, an obvious easy answer, or I should say base for this one is e. Okay, so I wanted to do one example using the new special base, but clearly there's no way we'd rewrite an irrational number. So in this case, we clearly just have e to a power equals e to a power. So obviously, because the bases are the same, the exponent 2x minus 1 must equal 4. So in this example, adding 1 and dividing by 2 gives us x equals 5/2.